we have the link to go to my math lab and stuff, the honor stuff. By the way, if you're interested in going from a regular section to honors, if you read the materials and you're comfortable enough, then send me an email, and then I'll send you an add code to add to honors. And if you're in honors and you want to go back, then you could do the same thing. Just send me an email, and my email is it's on the syllabus. I have 2 emails, and so I respond to one of them, and the other one I may respond, maybe not. R Lapuz 2, the one with the 2. I also have posted some information about the quiz stuff, and so you should finish up your peer reviews or whatever they're called by tonight. I couldn't find a way to have a due date for the peer reviews, so let's just say it's due tonight. And if you have issues, the solutions to quiz number 1 is online, and I also made a little video based on those cards that you guys had, the muddiest point cards. And so most of the people had issues with span, and the solution, the connection between AX equals B and systems and stuff like that. And so most of the muddiest point issues were covered in this video, so you guys can just watch that, take a look at it. So today we're going to start with section 1.5, and then we'll jump to 1.7, and then from there we'll see how far we can get. So we're still hovering around the idea of systems of linear equations, and so we're going to dig deeper into that, talk about different types of systems, and more importantly, the kinds of solutions that we're going to expect out of systems of linear equations. And then we'll see if we can make the connections to things like span and stuff like that. And then we'll jump to linear independence in 1.7. 1.6, by the way, are applications to systems of linear equations, and I don't feel like we need to spend too much time on that already, since we've already discussed systems. So I'd rather spend our time on more interesting mathematical things. All right. The first definition that's out here is called the homogeneous system. A system of linear equations is called homogeneous if, you know, the ax plus b equals, or ax equals b equation, if the b side is equal to 0. And you should also make a distinction between 0, the number, versus 0, the vector. And in this particular example, or the way it's written here, it's intentionally written as boldface 0. And if you're doing this by hand, instead of boldfacing your variables or 0, you would put an arrow on top of it to denote that it is a vector. So generally, if we're handwriting things, vectors have arrows on top, so we know it's a vector. And then things that are not vectors, which are called scalars, are going to be just a regular, usually italicized font. So the 0 vector in Rm, as you would probably guess, would be a vector with zeros, and then there would be whatever the dimension is. So if it's an R2, then it would be 0, 0. The 0 vector would be 0, 0. If it's an R3, it'd be 0, 0, 0, etc. So a system AX equals 0 always has at least one solution. It's guaranteed to have the 0 vector as a solution. And so that's because if you solve for that, right, you get 0. Now, there are some cases where you don't just get the zero vector as a solution. You might get more. And so that's the more interesting, well, I don't know if it's more interesting, but the interesting scenarios is that if we get a non-trivial solution, a solution that's not just the zero vector. It's clear that the zero vector is going to work, right? In fact, with scalars, if you had 3x is equal to 0, then x has to equal to 0. Yeah, x has to equal to 0. And that would be the only solution. But when we're dealing with matrices, it's quite possible that we get something that's not 0 that's going to be part of the solution. So let's take a look at possibility for a non-trivial solution. And if you remember in your readings, this whole idea of a pivot point, free variable, does that sound familiar? Okay, so we'll dig into that and hopefully it'll spark some memories of your reading. Then you'll get to know this information by heart by hopefully by the first exam. You know what a pivot point is and a free variable and stuff like that. All right, so let's take a look at this example. This example is taken from your exercise portion of the section in section 1.5. This is problem number 4. We have 5x1 plus 7x2 plus 9x3 is equal to 0 as one equation. A second equation, x1 minus 2x2 plus 6x3 is equal to 0. And they want to know if we can find a solution to that. Now, your solution x, by the way, the vector x is actually a vector x1, x2, x3. And those scalars, those numbers, are actually part of the system. So we can extract that and mess around with it and pull it out and make it look like a vector equation, stuff like that. But I'm hoping you're starting to see the relationship between these equations and those vectors and stuff. So if we pull the x's out, we can think of this as the matrix minus 5, 7, 9, and 1, negative 2, 6 multiplied by x1, x2, x3 is equal to, now the 0 vector on the right-hand side looks like it should just be a two-dimensional vector. And so if you go back to your idea of matrix multiplication, you have a 2 by 3 matrix that you're multiplying with a 3 by 1 matrix. And then your result then would, so the number of columns has to match with the number of rows. The number of columns for the first matrix has to match the number of rows for the second matrix. And then so you can see that they match. And then so this is a legal matrix multiplication. And then your result is just a 2 by 1 matrix, which is what happens here. So this is like your A, x equals b, where b happens to be the 0 vector. And then if you do the matrix multiplication, you'll get the system back. But anyways, that's kind of a long-winded explanation of the relationship between ax equals b and your system. But we want to get to actually trying to solve for this. And so let's see if we can actually solve for this. So we'll write this matrix in augmented form. We got minus 5, 7, 9, 0, 1, minus 2, 6, 0. And then we'll see if we can do some elementary row operations. I think maybe I might be interested, it's not necessary, but I might be interested in switching the rows. There's a lot of different ways to get the solutions, but I'll say I want to switch to row 1 and row 2 just to make my next step a little bit easier. So 1 minus 2, 6, 0, minus 5, 7, 9, 0. And then now I can just say I'm going to multiply the first row by 5 and add it to the second row, and then I'll replace the second row. So my first row stays the same, 1 minus 2, 6, 0. My second row becomes 0. That's the whole point, right? To make this into row echelon form. So 5 times negative 2 is negative 10, plus 7 is negative 3. 5 times 6 is 30, plus 9 is 39. And the last column doesn't change. So I think I could stop here and say, I can multiply the bottom row by negative 1/3 also to make it look a little nicer, but I think it's fine right here. So this is already in row echelon form. It's not quite reduced row echelon, but you can do whatever you want to do to make it a reduced row echelon form. So we have, usually we don't mess around too much with the augmented portion, and we look at the left-hand side portion of things and find pivot points, or pivot columns, I guess they call it. So to do that, we look at row by row. If we have zeros to start with, and we look at the first non-zero element, and the first the last row has a 0 on the left, and the first non-zero element is in the second column. So I'll have a pivot column here, and then I also have a pivot here. Okay, and that makes need an orange or something. Let's see if I can find orange. Yes. Well, I wouldn't call the -3 a pivot itself. I would call the second column a pivot column. So we're looking at the columns when we're identifying pivot columns. So we have a pivot column in the first and second. And then the third is also something to make note of. And I think I would call this a free variable. So x3, the third column, which corresponds to the third variable, is a free variable. So what does that mean when we have a free variable? It means when we're trying to find solutions for this, we can let x3 be whatever we want. Let it equal to 17, -2, 1/2, whatever we want. And then we're going to get a solution here for sure. So we have a free variable, and when we do have a free variable, we have a solution. There is a non-trivial solution. So we have a non-trivial solution. We should see if we can write it up. So if we try to write up our equation in reduced form, we have x1 minus 2, x2 plus 6, x3 is equal to 0. We have a -3. I should have divided by -3. -3 x2 plus 39, x3 is equal to 0. And we say that x3 is free. We'll say we'll let that be whatever we want. And then in the second equation here, we can say that -3 x2 equals -39 x3, and x2 is equal to, what is this, 13 positive? 13 x3. Did I do my math correctly there? If you have more than one solution, then Do you have a lot of solutions? We have infinitely many solutions. It's consistent. We can describe the solution as some sort of one parameter, as a parametric equation. Yeah, so there's ways to describe it. Yes. Yeah, it's either one or an infinite number of solutions, or zero. So those are our scenarios for our. We have we have infinitely many solutions because we have a free variable, and the free variable says that I can let this free variable to be whatever I want, and then all the other variables will depend on that free variable. And that means I can let it equal to 1, 2, 3, an infinite number of numbers, and there's your infinitely many solutions. Yeah? Yes? Yeah. Yeah, so the free variable has an infinite number of possibilities. I can let the free variable to be whatever I want it to be. So there's infinitely many choices. Yes, Thomas. Uh, you could have made it that way if you would have. You could have made it that way if you would have tweaked the way. If we would have tweaked like the way you solve for. If you didn't have it in row echelon form with the zeros on the left side, you could have made. You could have made 39 equal to 0 or something weird like that, and then maybe you could have let one of those other ones free variable. But in general, because we're doing the row echelon form, our free variable, you're going to start looking for free variables on the right side first. So x3 first, and then if x2 happens to be free, then you'll also deal with that free variable, and then you should have at least one pivot. Because you don't have a free variable in the pivot column. Yeah. So the weird thing is that you could tweak this so that the pivot is not in the first and second, but the first and third. But the way we set things up with the row echelon form, we usually have the pivot columns first and then the free variables last, whatever that means. Yeah. Because one is a leading term, yes. Yeah, zeros is 0. Yeah. Yeah, we'll do that when we start looking at the solutions. And then we'll take a look at a picture of this too. Then the whole bottom would be a row of zeros, in which case um, then it would be a whole row of zeros. Then you only have one pivot column and two free variables. No, for that case, there would still be an infinite number of solutions. If there was only one solution, the one solution would be your trivial solution, and then that's it. For homogeneous, so that's when it's equal to 0. When it's equal to b, then other things could happen. Yeah. Probably. That might be a quiz question for you. You guys have a quiz, by the way. Did you see it? Yeah. No, let's do next week. I don't know. Look it up. All right. So generally we don't want to just leave our equation looking like this. So let's see if we can clean this up and make it. Oh, we're not even done yet. We got x3 is free, x2 is equal to that, and then we still have to solve for x1. So x1 is equal to positive 2x2 plus minus, thank you, minus 6x3. And as you're looking at this, x2 is dependent on x3, so we can write x2 as something with an x3. So x1 is equal to 2 times 13x3 minus 6x3. So x1 can finally be written as in terms of the free variable. So what is it? 26, 20? So this is the set of solutions that we have that we can see if we can write this a little bit neater, because our solution, remember, has to be an x vector, right? It's not looking like a vector yet. But if we have a free variable in x3, I can write it in terms of x3. So your solution is going to be equal to 20 x3, 13 x3, and x3 is free. Okay. So your solution, remember the solution is going to be x1, x2, x3. And so I just replace x1, x2, and x3 with what we had found. And because x3 is a free variable, you can kind of take that out. And now what we have here is your solution that's written in, quote, parametric form. And like I was saying earlier, I can let x3 to be anything I want. And we can even change a variable and say, well, your solution is going to be t times 20, 13, and 1. And this would describe the solution set. All right, feeling a little abstract right now? Should get used to feeling abstract in this class. Let's visualize it. I think whenever we have a chance, an opportunity to visualize what it is we're doing abstractly, then that's great, because there's going to be some problems that we're going to do that we're not going to be able to visualize. But this is happening in 3 dimensions. And if you've taken Calc 3, then you have a little bit of an advantage. If not, then don't worry about it. If you have a good graphing program, you can visualize these things. So let's start with the original equations. Negative 5x1 plus 7x2 plus 9x3 is equal to 0, and then the other equation. Okay, so to visualize this, and if you have taken Calc 3, what are these equations supposed to look like? Do you know? These equations are planes. Okay. Except we probably use x, y, z instead of x1, x2, x3. So let's do that. For this, again, I used to use this program I really like a lot, but for these cases, I think for the sake of you being able to see this, if you want to try this at home, GeoGebra is free. So if you type GeoGebra, and then you can even sign in and save it as something that you would have, then that would be fine. All right, equations. What were the equations again? They were minus 5x plus 7y plus 9z is equal to 0. Okay, so what we have here is a plane. And the plane, not coincidentally here, passes through the origin. Let's get our second plane going. That would be x 2y is negative z equals 0. Again, a plane also passes through the origin. So we're guaranteed that point. This is a homogeneous system. It's equal to 0. We're going to pass through the origin. So I know for sure that that is a solution. Okay? So what did we find? We found this vector. We found this vector 20, 13, and 1. So if we treat that as a vector, that would be a vector from the origin to that point 20, 13, and 1. So what's so interesting about that point? Well, let's take a look at the point first, and then we'll take a look at the vector. What's interesting about that point? If we put a point, let's call it P1 point. Looks like I could put 20. I think I had this issue. Was it in this class? Twenty, 13, and 1. Did it work? I don't know. Where is it? Oh, this only goes up to 7, negative 7. So we need to do some zooming out here. Oh, that's zooming in. There's that point. Make it red. Make it bigger. It's not red. Well, in any case, it looks like it passes through the origin. It passes through those two planes, right? That's a good sign. Now, according to my solution set, if I let t equal to 0, wait, what happens if I let t equal to 0? That's a solution, right? 0, 0, 0. That's a trivial solution. We know that that's a solution. If I let t equal to 1, I get this. But if I let t equal to 1/2, it's not so nice. This is divided by 1/2. So let's find another point. So 10, comma 13 over 2, comma 1/2. Does it look like it's still on both planes? It looks like it's still on both planes, right? Actually, if we can get rid of the xy plane, just so we can see just the two planes. Okay, so it looks like if I change the value of t, I'm still going to be in the intersection of those two planes, which means I'm still going to be a solution for this system. Yeah. I have to make up a whole new problem for that. Yeah, we could. Let's see. Let me just do one more thing here. P equals 20 times t, 13 times t, 1 times t. That's undefined. Let's try to put a slider. I don't know how to do sliders here. Ah, thought I knew how to do this. Undefined. I need a slider. Anybody know how to do a slider in GeoGebra? Anyways, let's pretend it's drawn. And what's going to happen is that no matter what value of t I choose, I'm going to continue to be in the intersection between those two planes. That's what I was trying to say. It would have been nice to see it. Because that was the solution that we found. We found a solution as t times 20, 13, and 1. So regardless of what value of t I have, I will be on both planes at the same time. And that's how the solution is described. All right, one more try, and then I'm going to let it go. And I think I need to put this one after that. That work? There it goes. So regardless of what value of t I choose, I will be in that intersection. So these two planes look like they intersect in a line, and then whatever value of t I choose will be that you'll have a vector that's going to be on that line. All right, good. Thanks, Malcolm. Let's take a shot of this, put it in our notes for you guys to view. And I think I can, if you want to mess around with this, let's see if I can do this. I have to save it. Well, in any case, I think I'll do this later. I think I can create a link so that you can go to the same page with this already set up and then play around with the slider. Okay, so that's our example for finding a non-trivial solution. To come up with a really simple example of something that might not have a non-trivial solution, let me just make one up. It's always bad to make something up. Yeah. So x1 plus negative. Wait, is that? What's the last number? 23. So that's either a how do you say it? Non-homogeneous, or you have 4 variables, in which case it'll be trickier, yeah? We could do that. What was the equation again? The first two? So if we're going to come up with a third equation, the only thing we need to make sure is that it's not going to be the exact same plane as the other two, which is, which is a more, anyways. So let's put 0 plus x2 plus 3x2 minus, I guess we don't need a plus there. Minus 10x3 is equal to 0. So here I have 3 planes, and so if we change this into a matrix, yeah, minus 5, 7, 9, and 0, the augmented part. 1, negative 2, 6, and 0, 3, minus 10. So we could do the same. Should we go through the order? Yeah, let's go through. So we'll switch row 1 and row 2. 1, minus 2, 6, minus 5, 7, 9, and 0, 3, negative 10. Now, later on, we'll see that, packing on these zeros, if you know that your system is a homogeneous system, we don't need to keep writing the zeros, because whatever we do in our row operations, it's always going to be 0 on the right-hand side anyways, right? So we're going to slowly get rid of that and kind of start ignoring it. Anyways, I think last time we did a 5 times R1 plus R2. So we have 1, negative 2, 6, and I'm going to start ignoring the zeros now. What was this? 0, negative 3, 39? We could, or we could just, I'm going to need to knock out this other one anyways, so I purposely chose a 3 for this one so that I can take it out. And then here I'll take, well, I'll just add row 1 plus, or row 2 plus row 3 and replace row 3, and that would make the last row 0. There's usually you want nice numbers to multiply by and then add to this first row. And remember that the whole point in doing this is to get row echelon form. So we have row or zeros on the bottom left-hand corner of your matrix. So the switching rows is really just whatever you think might be more convenient. Somebody suggested I multiply this by negative 1/3 to make that into a 1. That also would have been a good move. If this thing was more complicated than a 3, I probably would have done that. But since I made this into a 3 so that I know it's going to be 0, then I think leaving it at 3 was fine. This is whatever this is. I think we just added. So this is 29. And so this is your system that's reduced. And if we just write this out, we have x3 is equal to 0, or let's say 29 x3 is equal to 0, but that would just say x3 is equal to 0 anyways. Oh, first of all, there are no free variables, right? And second of all, we have a pivot. In each column. So there are no free variables. There's a pivot in each column, so it looks like this is going to turn out to be the trivial solution only. We have x3 is equal to 0, and then we have minus 3x2 plus 39x3 is equal to 0 via the second row. But x3 was equal to 0, so we got 3x2 plus 0 is equal to 0. So we see that x2 is going to be equal to 0. And then likewise, x1 minus 2x2 plus 6x3 is equal to 0. But we know that these are all equal to 0. So all you have is 0, 0, 0, trivial solution. And then that's that. And if we were to graph these 3 planes, you'll see the only intersection that they will have would be at the origin. Okay. Questions? All right. Onward. So parametric form, we've kind of talked about this already. If you have a free variable, that free variable will act like a parameter, and you can write your equation as a parametric form, in parametric form, and then you can either keep the x3 or whatever the free variable is as is, or you can change it to a t, usually a t or an s or a u or a v. Those are a standard standard letter variables that we use for those parameters. So parametric vector equation is an equation that expresses linear combination of vectors with weights given as the given parameters. So your scalar constants are the parameters, xt or t. In fact, again, if you've taken Calc 3, you've studied maybe even pre-calculus, some pre-calculus, you might have studied parametric equations. And if you have a parametric equation, you can draw out a line or a plane or whatever. Let's take a look at a non-homogeneous Let's take a look at a non-homogeneous system. So a non-homogeneous system is a system that looks like AX equals B, where B does not equal to 0. So if you have a system AX equals B where B is not equal to 0, then you have a non-homogeneous system. So you got the difference between homogeneous and non-homogeneous. So suppose the equation AX equals B is consistent. That means you have a solution for some given B, and let P vector be a solution. Then the solution set is going to be all the set of vectors W is equal to, starting off with P plus a V sub H, where V sub H is a solution to the homogeneous system. What? What? All right, let's take that example that we were working on, since we already know the vector solution for that, and let's make it into what should we call it? A non-homogeneous system. So example, we have tell me what it is again. And then I'm going to write it backwards. Go ahead. All right. So those original equations that we saw had zeros in them. So let's now change it so that it's not equal to 0. So let's shift the two planes in different places. So let's pick a number, 5, and then pick another number, 0, 3. Let's do 5 and 3. Now let's take a look at this. Graphically, since we do have a graphing device here, let's set up another one. x minus 2y plus 6z equals, what was it, 5? Negative 5x. Yeah. So we see that these two planes no longer hit the origin. They've been shifted. So that's out. We can't use that. That's not a solution anymore. And that point wasn't a solution anymore. So that point doesn't intersect both of these graphs anymore. Okay. So what can we do? Well, according to this, we need to find a solution to this non-homogeneous system. So we need to find one point that would satisfy this system. Let's see. 1 minus 2, 6, 5, minus 5, 7, 9, 3. And so the work that we're going to do is essentially the same, except I switched these so I don't have to do that first row operation where I switch to rows. So now I just have to multiply the first row by 5, add it to the second row. And then I get 0, minus 3, and 39 again. Those are the same values because that's the same kind of move that I made. So now 5 times 5 is 25, plus 3 is 28. So I still get a free variable, it looks like. Free variable in x3. I have pivot, pivot. So I can structure my solution a certain way. I can say that minus 3x2 plus 39x3 is equal to 28. And then I would probably, I need to solve for x2. I know my x3 is free. So I need to find x2 and x1 so I can create my solution. So x2 is going to be 28 divided by negative 3 minus plus, whoa, minus what? What happened? I need to take a picture of it when it's blue so I can complain. Actually, I should be complaining here. This is not the right colors. All right. So I have a constant, 28 over 3, or negative 3, and then I have 13x squared, or 13x3. That's what my x2 is equal to. My x1 is going to be 5 minus 2 plus 2x2 minus 6x3, and then I'll drop the information for x2. So x2 was negative 28 over 3 plus 13 x3 minus 6x3, and then we just need to combine. So x1 is going to be 5 plus minus 56 over 3, so 56 minus 15, 41. 41 thirds. And then I have 26 minus 6 is 20. Hopefully that's right. All these fractions. Okay. So now I want to lay it out like a vector, x1, x2, x3. So your x is equal to x1, x2, x3. And this is equal to x1. Well, this looks messy. Negative 41 thirds plus 20 x3. And then x2 is equal to 28 thirds negative plus 13 x3. And then x3 is free, so that's just x3. So if we peel this apart, we can take a look at the constant terms plus numbers times x3. So we can actually split this up into a couple of vectors. One is a vector of constants, negative 41 thirds, negative 28 thirds, and 0, plus, hey, look at that. That looks familiar, right? So the second number over here, 20, or the second vector, 20, 13, and 1, was the same vector that we saw in the homogeneous portion of things. So it looks like we have a particular solution here. And then we have another parameter family. So those two planes that we saw intersected in a line, right? Except the line doesn't go through the origin anymore because it got shifted. So where does it go through? It goes through this point, negative 41 thirds, negative 28 thirds, and 0. So if I were to plot that point and see where it is, it should be within the intersection of those two planes. We'll do that in a minute, but can you look at this and see if it makes sense? Do you have any questions? Yes. Say it again. Oh yeah, because they say, well, they say it in a theorem, but the idea is that the difference between homogeneous and non-homogeneous is that the right-hand side is equal to 0 versus not equal to 0. But you still have the same structure. And so the structure just got shifted out of the origin. And so now, instead of your solution just being equal to that, it got shifted somewhere else. So it got shifted by adding this thing. Okay. Any other questions? So if we take a look at the solution that we have, if we let x3 equal to 0, remember I can let x3 whatever I want. If I let x3 equal to 0, then all I have is that constant vector, which is one of the solutions. Okay. So if I were to find that point on this graph, it should be somewhere in the intersection. So they call that point P in the theorem. P. So P equals some point, and what is it, negative 41 over 3, negative 28 over 3, and 0. So this is this point right here, right? So now if I want to draw a vector, if I want to add those two, nothing's happening. Where's this point? Oh, I need to put the input. P plus T times VH. So you can see that whatever value we choose for your parameter, we're always going to be in that intersection, even if the things got shifted. Okay? All right. Any questions? Whew. Solutions to systems. So basically, if we want to summarize this whole process, whether we're dealing with homogeneous or non-homogeneous systems, what we want to do is we want to write your system into a matrix, an augmented matrix, and then do the row echelon form. If you could do the reduced row echelon form, even better. Express your basic variables in terms of any free variables appearing in the equation. So in the example that we've been working on, we had one free variable, x3. So what we want to do is write x2 and x1 in terms of that one variable x3. And then write a typical solution for x as a vector whose entries depend on the free variable. So I'd write x is equal to, and then in x1, I'll have the expression with an x3 in it. In x2, I'll have the expression with an x3 in it. In x3, I'll have the expression with an x3 in it, since that was our free variable. So that's what we were doing over here. We're writing our solution as x1, x2, x3, but instead of x1, x2, and x3, we're going to write it in terms of what x1 is equal to, something with an x3 in it, etc. And then decompose x into a linear combination of vector with numeric entries and using a free variable as a parameter. So this is a vector with numeric entries, and then this is your free variable with the vector multiplying. Okay? So that's how you would solve for these systems. All right. Oh, we have 10 minutes. We can do one more section. So let's go into the next section that we're going to cover, linear independence. And we'll start off with the definition. So if you have a set of vectors, the set of vectors is said to be linearly independent if you can write a vector equation where essentially a linear combination of the vectors with some weights, x1, x2, etc. And the only solution that you get there is a trivial solution. Since we were just talking about trivial solution, that means if you try to solve for this, the only x1, x2, x3 values that we're going to get would be all zeros. There are no free variables. The set is said to be linearly dependent if you can find values that are non-zero, at least one, maybe two, of those weights that are not equal to zero. If you could do that, then those things are dependent. So graphically, it's best to look at a two-dimensional example. We could also look at a three-dimensional example. I think it's easy enough to see, but so in 2 dimensions, oops, I'm still at the highlighter. So in 2 dimensions, if you have 2 vectors, and if you can write this as a linear combination that would equal to 0, and then we can find values, non-zero values, if we can find non-zero values to put in there, I mean, if I put 0 and 0, that's a trivial solution. It's going to work, right? Can I find 2 numbers to put in these blank spaces? Say it again. 1 and -1/2. Would that equal to 0? So I found non-zero values for this. So that means that these two are linearly dependent. Okay. So you could also think 1, 1, 0, 1. And then again, if we can come up with 2 numbers that would make this 0, 0 that are non-zero, then it would be linearly dependent. So can you find 2 numbers? No. The only numbers that would work are 0 and 0. And that's a trivial solution, right? If you let one equal to be 5, then the other one, yeah, there's no way to get 0. Okay? So these two are linearly independent. So graphically, what happens is that if you have 2 vectors, if they are linear combinations of each other, we can also think of this as 1, 1 plus or equals. If we can write one as a scalar multiple of the other, then we're just saying that we're scaling this. And so if we put 1/2 there, that'll work. So it's the same kind of idea as writing it as a linear combination. How's that look like with vectors? How do you do vectors here? That's a vector 1, 1. And this is a vector 2, 2. So if those two are aligned, then they're dependent. So if we compare that with our third vector, these two are not going in the same direction, so they're linearly independent. What if I throw a third vector there? What if I throw a third vector? So it'll have to be linearly dependent. So what if my set of vectors is 1, 1, 0, 1, 1, 0. So the question is, can I write this as a linear combination and get this to equal to 0 by putting in numbers that are not all equal to 0? Because clearly if I put zeros in there, that's a trivial solution. Anyways, can you find me some numbers that would make this equal to 0? 1, -1, -1. Agreed? You could probably find more, right? You find other combinations of numbers. So in any case, if I have 1, -1, -1, I'm going to get this to equal to 0. So I'm guaranteed, how should we say this? I'm guaranteed to find a non-trivial solution. A non-trivial solution. So think about the number of variables that were here. These blanks can be considered as x, y, z, or x1, x2, x3. Think about the number of variables we have, and then if you piece this out into separate systems or separate linear equations, you can see that this corresponds to a system of linear equations. All right. There's more to be said about linear independence, and maybe we'll talk a little bit more about that. But next time we really need to dive into the next section, which is linear transformations. All right, so you guys have some work to do, quiz and homework or something like that. Homework due on Sunday. So good luck. Oh, the last chance to do a peer review is tonight, so you need to finish that up also. And if you don't do 3 peer reviews, then I'm going to take off points from your quiz.